let's go ahead and see. Are we online? Let me refresh the page. Okay, I can see my setup. And I can hear myself. Do I see my hand? Yep, it's showing up. Okay, everything is looking good. So let's go ahead and get started. Let me put the headphones away first. Alright, so I don't really know what it is I want to do today, but I'm thinking of just continuing from where we left off last time and introducing capacitors, and maybe, depending on how long that takes, we might go over some mechanics stuff later. I have a couple of things in mind that I've been wanting to make individual videos on for a while, but I haven't gotten around to that, so maybe I'll just do that today instead. But we'll see. So, let's see. Capacitance. What do I want to do as far as capacitance is concerned? I guess we can start off by defining capacitance. Let's go ahead and do that. So, defining capacitance. Let's see. Capacitance is equal to the total amount of charge you can separate between two metal surfaces over the change in electric potential required to separate that charge, which might be a bunch of mumbo jumbo to those of you who haven't seen capacitors and capacitance before, but we'll elaborate on that. So let's go ahead and start with the most classic type of capacitor, the parallel plate capacitor. So I'm going to have two metal plates something like this. They're going to have some sort of area A. They're going to have some sort of area A. And they're going to have, well, they start off uncharged. They start off uncharged. Just two plain old sheets of metal with a little bit of a distance between them, D. And what you do is you hook this thing up next to a battery. You hook this thing up to a battery. So here's some wires. Positive end of a battery, negative end of a battery. And what this battery does is it produces some sort of difference in electric potential, some sort of change in voltage across the two different plates. So what ends up happening is positive charge ends up developing on the surface of the top plate, the part that's connected to the positive end of the battery, and an equal amount of negative charge develops on the bottom plate. Basically, electrons move from the top through the wire to the bottom. So whatever total charge is on the top plate, a charge of equal magnitude exists on the bottom plate, and the magnitude of that charge is the Q in this equation. So now we want to figure out what is the ratio of charge separated to difference in potential between the two plates? Well, once this thing is fully charged up, there is going to be a charge of positive Q on the surface of the top plate and a charge of negative Q on the surface of the bottom plate. We can use Gauss's law, or at least the conclusion that we've been using for the past couple weeks from Gauss's law, to figure out what the electric field is in between these two plates. There's going to be some electric field that points from positive to negative charge, so there's going to be an electric field like that. There's going to be an electric field pointing from the top plate down to the bottom plate, and we can calculate the difference in potential by taking the integral of this electric field. Our voltage, or change in voltage, is going to be negative integral of E dot dl. If we treat these two plates, if we approximate them as infinite sheets, then we can say that the electric field due to the top plate is simply E top equals sigma over 2 epsilon naught. And same thing for the bottom plate. We can say that the electric field due to the bottom plate, E bot, is equal to also sigma over 2 epsilon naught. It'll be the same amount of charge over the same amount of area. Sigma equals Q over A. Let's see, where do I want to go from here? So I guess now I want to specify the directions of the electric fields. So electric field due to the top plate is going to point away from the top plate. For the region in between the plates, that's going to be down. And then the electric field due to the bottom plate is also down. So those two electric fields due to the top and bottom plates must add up. So the total electric field that we need to plug into our integral will have a magnitude of E top plus E bottom, 1/2 sigma over epsilon naught plus another 1/2 sigma over epsilon naught. E total has a magnitude of sigma over epsilon naught equals Q over A epsilon naught. Okay, plug that into here, and what do we get? So integral of, or negative integral of E dot dl becomes negative integral of, well, E is down, and we're integrating from L equals 0 to L equals D, right? The distance between those two plates, we're just integrating in a straight line. So the dot product just becomes a regular product. You're just multiplying the two quantities and the cosine of 0. The direction of the electric field is in the direction of the path we're integrating over. So it just becomes Q over A epsilon naught integral of dl. All this stuff is constant, so it can be pulled out of the integral, and then the integral of dl from this point to this point is just that distance d. So we're left with negative Q over A epsilon naught times D for our voltage. The negative tells us that the voltage at the bottom plate is this much less than the voltage at the top plate. but overall it's the magnitude of the difference that we care about for a capacitor, so that negative sign can be ignored. So to calculate the capacitance, finally, we just do capacitance equals total magnitude of charge separated over the change in voltage required to separate that charge, which we now know has a magnitude of Q over A epsilon naught times D. The amount of charge separated cancels out, so it doesn't even matter. And that leaves us with epsilon naught times A over D, if you simplify that complex fraction. Okay, so if you've already seen capacitors in class, then you've probably been told that capacitance is solely a function of the geometry of the capacitor, and this is proof of it. You've got a physical constant, and then the only other factors are area and distance. Those are all about the geometry of the capacitor. So for the parallel plate capacitor, this is how we define its capacitance. Okay, that's all fine and dandy, but what about other types of capacitors? What if we had, for example, a spherical shell capacitor? Let's go ahead and take a look at how that would work. So let's say I have how do I want to draw this? I want to keep the thing somewhat open. So I want thin spherical shells. Okay, so that's an open sphere, and then essentially what I want to draw, what I'm trying to show here, is a pair of hollow spheres, a smaller one inside of a bigger one, both made of metal. Capacitors have to be conductors. And let's see, I'll give this one a radius of A, and then the outer sphere will have a radius of B. And let's figure out how the capacitance works out for something like this. So I guess I'm not sure how I would illustrate the battery connecting to the inner sphere in this case. I guess you could say that the wire is wrapped in like rubber or plastic through a hole inside of the outer sphere, connecting it to the inner sphere. We could say something like that. We could assume something like that. I mean, I don't need to draw the battery here, but let's say that I did. Let's say that this connects to the negative end of the battery. It doesn't really matter too much which side is the positive and which side is the negative, but there we go. Let's say an amount of charge Q develops on the surface of the outer sphere, positive Q, and then you get negative Q on the outer surface of the inner sphere. Well, the outer surface is the only surface that either of the spheres have because they're hollow. But you get what I mean. what is the difference in voltage between those 2 points? So, no, I don't want to use green for this. Let's use yellow. What is the change in electric field in going from here to here? Or, not change in electric field, what am I saying? Change in electric potential in going from this point to this point. We have an electric field that's going to be from the positive to the negative, as electric fields always point. They always point away from positive charge and towards negative charge. And we want to integrate along this path. So let's go ahead and write down what we know. We know the total charge on the surface of the outer sphere is Q. And on both surfaces it's got a magnitude of Q. I'm too disoriented today, I guess. I can't even speak straight. Let me just write things down and I'll comment after I write. So let's see. We want to define sigma outer for the outer sphere is going to be Q over, let's see, the area is going to be 4 pi b squared. Surface area of a sphere is 4 pi r squared, so that's for the outer one. And then for the inner one, sigma inner is equal to Q over 4 pi a squared. Okay, and then if I want to figure out my change in voltage, I guess I'm going to have to first determine what the electric field is in the space between A and B. So let's go ahead and do that. We're going to need Gauss's law for that. Which color? Let's go with orange. So I want to do a Gaussian surface, a Gaussian sphere in this case, of radius between A and B. Let's see, so total flux integral of E dot dA. I was about to say dr for some reason. Integral of E dot dA equals charge enclosed over epsilon naught the E can be factored out. The dot product just becomes a regular product because the direction of the electric field is just going to be, well, I guess in this case the electric field points inward, so we should actually have a negative sign. The dot product would give us a cosine of 180 degrees, so that's where that negative is going to come from. And then we're left with just the integral of dA, which is just going to be the total area. And the total area for a sphere of radius r between A and B is just going to be 4 pi r squared equals the charge enclosed is negative Q over epsilon naught. I guess I didn't actually need these surface charge densities then. Those negatives will cancel out. And E times 4 pi r squared equals Q over epsilon naught. So E is equal to Q over 4 pi epsilon naught times 1 over r squared for r between A and B. I would try to find it for other regions of interest, but we don't need it. Actually, for other regions of interest, it would be easy. It would be 0 for a radius less than a. Your charge enclosed is 0, and for a radius greater than b, wrapping around both spheres, total charge positive q plus negative q is again 0. So actually, the only place where electric field would exist for this setup is in the space between the surfaces of the two shells. Okay, now that we have a formula for our electric field, we can go ahead and integrate that electric field with respect to, I guess, R, in order to get our change in voltage. Change in electric potential is equal to negative integral of E dot dl. E is going to be in the inward radial direction, and dl I'm going to be integrating also radially inward. So dl is just in the direction of change in R. So it's going to be, let's see, negative integral of, well, hold on, dr. R increases from the center and outward, so the direction of dr is outward while the direction of the electric field is inward. So actually we should be getting E dot dr would give us E times dr times cosine of 180, so we would get another negative sign which would cancel with this one, and we're left with q over 4 pi epsilon naught times 1 over r squared dr. And we're going from r equals b to r equals a. All this stuff is constant and can be pulled out of the integral. So we've got q over 4 pi epsilon naught times integral of 1 over r squared dr. That's just going to become negative 1 over r. Negative 1 over r evaluated from b to a equals q over 4 pi epsilon naught times negative 1 over a minus negative 1 over b, or I could also write it as 1 over b minus 1 over a. 1 over b minus 1 over a. And that quantity would be negative because 1 over b is smaller than 1 over a. b is a larger denominator, so this would be a negative quantity, which makes sense. The voltage should decrease if you go from the positively charged surface towards the negative charge. Voltage goes down as you get closer to negative charge, so that's all consistent. But again, it doesn't matter here because just like before, we only care about the magnitude of the voltage in this case for determining the capacitance. So, capacitance equals total charge separated Q over the total change in voltage required to cause that separation. Let's see, if I want just the absolute, or I can't talk today. If I wanted just the absolute value of this voltage, then I would change this to 1 over A minus 1 over B so that it would come out positive. Anyway, that's Q over 4 pi epsilon naught times 1 over A minus 1 over B. The Q's cancel out. And so we have 4 pi epsilon naught over 1 over A minus 1 over B. I can rewrite as, let's see, multiply this by B over B and multiply that by A over A. So I get B minus A over AB. And then we can simplify that even further. So we've got 4 pi AB epsilon naught over B minus A. And there you go. Once again, capacitance is merely a function of the geometry of your capacitor. All of these terms, well, at least all the variables in here, A and B in this case, are just geometric properties of our capacitor. In this case, the inner and outer radii. Okay, let me see, what else do I want to do with this stuff? I guess we could also do the case for cylindrical capacitors, but I think you've seen enough to be able to figure it out with cylinders. Do we want to do capacitor circuits? I mean, I feel like that stuff is simple enough that you don't need me to do it, but yeah, I'm not sure. Let me look at these problems and see if there's anything interesting. I guess we could talk about dielectrics, but dielectrics don't do anything too hard to figure out. If you have a dielectric, then you just multiply the capacitance by some constant factor and you're done. Well, they do talk about the effect of adding a conductor. I guess we could comment on that a little bit. Okay, what happens if I add a conductor? Between the two plates of a parallel plate capacitor. So here's another parallel plate capacitor for us, but this time I'm going to slip a conductor in between. So I'm going to have a metal slab we'll draw it like so. And come to think of it, I guess I didn't really finish that slab properly. Okay, now it looks more three-dimensional. Okay, so suppose this is what I have. Suppose I've got positive charge here on the top and negative charge here on the bottom, and I've got this metal slab that I just decided to stick in the gap in between the two capacitor plates. What effect does this have on the capacitance, if any? What effect would this have on the capacitance? So essentially, the only effect it would have is it would be the equivalent of shrinking the distance between the two capacitor plates. If we remember from earlier, capacitance for a parallel plate capacitor is epsilon naught A over D, where D is the distance between the two plates. But this time we've got a conductor sitting in between them, so this changes things a little bit. Let's say that this thing has a height of h, and let's see what effect that would have on our system. So we know that the electric field inside the bulk of a conductor is going to be 0. Electric field equals 0 in here. And what that does for us is it interrupts our integral when we're calculating the change in voltage between the top plate and the bottom plate. Because now you've got electric field here, and then nothing, and then the electric field continues down here. So essentially, what this is doing is it's changing our voltage. It reduces the total voltage. We would be integrating from, I guess I'll label the points A, B, C, and, oh, I don't want to call it D because that's already D. Okay, we'll call it E. So essentially, instead of integrating all the way from A to E, we're integrating from A to B, we're skipping B to C, and then we're integrating again from C to E. So essentially, we're integrating over the same distance minus the distance from B to C, which adds nothing to our voltage integral. So this time, the overall change in voltage from A to E is going to be, let's see, negative integral E dot dl just becomes E times dl the E is a constant that can be factored out, and the integral of dl is just going to be d minus h. And E, if you remember from earlier, was not that, there. E total was just sigma over epsilon naught, which is Q over A epsilon naught. Times D minus H. And finally, we just go back to the definition of capacitance. I guess I'll use absolute values here just to make that extra clear. Absolute value bars. And which color do I want? Let's go for green. All of these markers are going to need to be replaced soon. Maybe next week I'll have some new colors to show you guys. Let me see, where was I? So if I do Q over A epsilon naught D minus H, then that will give us, Q's cancel out, epsilon naught A over D minus H. And there we go. So slipping a conducting slab of metal in the space between a pair of charged parallel plates will reduce their capacitance. Wait, reduce? No, actually will increase their capacitance by essentially reducing the change in potential, and that reduction in the change in potential is proportional to the reduction of the distance between the two plates. That reduction being the thickness of the slab. So yeah, if you're dividing by d minus h, you're dividing by a smaller denominator compared to before when the denominator was just d, so you get an increased capacitance overall. Total charge is the same. What you've done is you've reduced the total change in voltage. So higher capacitance overall. And then dielectrics kind of have a similar effect. Dielectrics will reduce the electric field between the plates. They'll produce an electric field pointing in the opposite direction so that the total electric field between the plates is lower, and that is yet another way to reduce the change in voltage between 2 points, since the voltage depends on the strength of the total electric field. But otherwise, dielectrics aren't too hard to work with. Usually, dielectrics are supposed to fill in the entire space between the surfaces of your capacitor. But there are cases where they give you something like this problem over here. I guess we can take a look at it. First, let me give a formula. So, capacitance with a dielectric. Is there a special symbol for it? I don't think so. Capacitance with a dielectric, I guess I'll call it C star, is equal to the default capacitance of a capacitor multiplied by Greek letter kappa, kappa being the dielectric constant. Dielectric constant of the material that's being stuffed into the space between the plates of a capacitor, assuming it's a parallel plate capacitor to begin with, between the surfaces, I'll call them, of a capacitor. And that dielectric constant will depend on the material, of course. Different materials are going to have different dielectric constants, so some might be more effective than others at increasing the capacitance. But overall, it's just a simple multiplication. So, if I have the following scenario, if I have a pair of parallel plates and I stuff only half of the gap in between them, if I only put a dielectric material that covers up, or that takes up half of the space between the two plates. what is the new capacitance of this capacitor if it started with a default capacitance of, we'll call it C0. And again, we'll call this D. And we will say that this is, I don't even have the space for it, that is D over 2. The thickness of our dielectric is D over 2. So I guess before we discuss how this one works, we would want to talk about combinations of capacitors. Essentially, the trick to solving something like this is to treat it like a pair of capacitors that are connected to each other in series. Essentially, what we want to do here is treat this like, and I don't know if I have enough space. Actually, maybe I can draw it in the space over here. We want to treat it like so. We want to treat it like one parallel plate capacitor with no dielectric in between, connected through wire to another parallel plate capacitor that does have a dielectric material in between. And I guess I'm going to use green to represent my dielectric material. There we go. We're going to treat it like a pair of capacitors connected to each other in series. So I guess before we proceed with solving this problem, what I would want to do is go ahead and prove the formula for adding capacitors in series. Let me go ahead and call that distance d over 2, and this distance is also d over 2. And let's see. Formula for the combined capacitance of two parallel plate capacitors. How would that work? If I have two parallel plate capacitors connected to each other directly through a wire, I don't think I'm going to have enough space to illustrate this here, but I'll try. If I have one pair of plates like so, connected to another pair, and then both of those are ultimately connected to a battery, then what's going to happen as these capacitors charge up is some electrons are going to leave this top plate, and they're going to go through the wire, travel through the battery, and then come back here and start gathering on this side. So you'll start getting negative charge developing here. And this negative charge that develops on this bottom plate, on top of leaving behind a positive charge here, it's going to repel the negative charges on the top plate of the second capacitor. So the negative charges from this second capacitor are going to want to move away, and they will move away to here, leaving behind some positive charge over here. And the total charge that leaves this top plate is going to equal the total negative charge that hits this lowest plate which is going to be equal in magnitude to the positive charge left behind on this third plate, which is going to be equal in magnitude to the negative charge that gathers on the second plate. So essentially, what I'm trying to say here is that if two capacitors are connected to each other in series, then the total charge displaced for both of them must be the same. The same amount of charge must be separated for each pair of plates. So Q on this plate must equal Q on this plate. So the charge is the same for both of them. So if they happen to have different capacitances, then what must be true for them is that their voltages are different. Their charges have to be the same, so if there's any difference between them in terms of capacitance, it's a difference in voltage between the two. So if I wanted to replace these two capacitors with a single capacitor that has the same overall capacitance, then they would have to be replaced with a capacitor whose total separation of charge has a magnitude of Q, and whose total change in voltage between the two plates equals the sum of the change in voltage for each of these two. So there's going to be some sort of delta V, I guess I'll call it delta V1 over here, and there's going to be a delta V2 over here. And if I want to replace these two capacitors with a single one, then I want to have the same total charge, which is already the case for the original capacitors, and the same total voltage. So I want the change in voltage here, delta V total, to be delta V1 plus delta V2, delta V1 plus delta V2. Okay, if that's going to be the case, then rearranging the equation for capacitance, I can say that this new capacitor, let's see, if I solve it for delta V, I would do Q over C. So the new capacitor is going to be, delta V total is going to be Q over, I guess I'll call it C total, equals Q1 over delta V1, or no, wait, what am I saying? I should say Q1 over C1. Delta V1 is Q1 over C1 plus Q2 over C2. But Q1 and Q2 are the same, so they're just Q, and those Q's cancel out, and we are left with the equation for combining capacitors in series. 1 over the total or equivalent capacitance, as it's usually called, is equal to 1 over the first capacitance plus 1 over the second. And I guess I haven't defined what it means for two things to be connected in series, so I might as well talk about that definition as well. Two things are in series if you travel along a wire, and if you cross one device, you cannot continue without crossing the other device. Over here, if I go through this capacitor, then I'm railroaded into going through this second capacitor. I can't take a detour to avoid running through both capacitors. You either run through both or you run through neither. as you travel along the wire. If there was like a branch over here, if there was like a branch that allowed you to skip past the second capacitor, then they wouldn't be considered in series anymore. Series is when going through one requires you to go through both. Two things are in series if going through one of them means you cannot avoid going through the other one while traveling along the wire. You don't have any other branches in your circuit that you can take where you'd be allowed to go through one and not the other. The other case we will come across is devices connected in parallel, and a lot of students get confused on the meaning of parallel. Parallel does not mean that they are geometrically drawn parallel to each other. So I guess I'll draw in this empty space over here, I'll draw a circuit. Let's say we've got battery here, and then I'll draw a branch over here with a capacitor, and a branch over here with a capacitor like that. Now, a lot of times when you have a circuit like this, the second capacitor would actually be drawn over here instead. And you would look at it and go, oh, well, they're drawn parallel to each other, so that's how we know they're parallel. While we do tend to draw things parallel to each other when they are in parallel, we don't have to. These two capacitors are still in parallel regardless of how this looks geometrically. What makes these two capacitors in parallel is that once I get to this point, traveling through the circuit, starting from the battery, once I get to this point, I have to choose either or. I cannot choose both. I can either go down this route and then circle back to the battery, or I can go down this route and circle down and around to the battery. You can't do both, or at the very least you don't have to do both. I guess you could theoretically have some electric charge traveling around like this and going this way in that square, but that doesn't have to be the case. So two paths or two branches on a circuit are considered to be in parallel to each other if the charge traveling through the wire has to choose between one or the other. Charge can't be in two places at once. What you could have is like some total amount of charge and some fraction of it goes here while another fraction of it goes here. But the point is, whatever fraction of charge decides to go down this branch cannot go through here, and vice versa. Any charge that gets to this point has to make an either-or decision, and that either-or nature of it is what makes these two branches parallel. You have this as a starting point, you have this as an ending point. Any charge that wants to get from this point to this point has to either go this way or go this way. So those two routes are parallel. Anyway, we've just gone ahead and shown the equation for finding the equivalent capacitance for capacitors connected in series. So let's go back to our problem of dielectrics. So we have a dielectric in here that only fills up half the space between the plates of a parallel plate capacitor. So we can think of this as being the equivalent of two capacitors in series, one with a dielectric and one without. Let's see, how would we go about doing this one? So if I have cut this distance in half, then according to this equation, cutting the distance in half doubles the capacitance. So this would have a capacitance of 2C0. This first capacitor would have a capacitance of 2C0, while this one would have a capacitance of 2C0 times the constant for this dielectric material. So this one would be 2 kappa C0. And from there, we can calculate the overall capacitance. 1 over equivalent capacitance is equal to 1 over 2C0 plus 1 over 2 kappa C0. Let's see. I can multiply everything by 2 to get rid of the 2's at the very least. And I guess if I factor out 1 over kappa, then this becomes, let's see, 2 times 1 over C equivalent is equal to 1 plus 1 over kappa times 1 over C0. And 1 plus 1 over kappa can be rewritten as, well, the 1 can be rewritten as kappa over kappa. So this becomes kappa plus 1 all over kappa. And where do I want to go from there? Let's see. 2 times 1 over C equivalent equals kappa plus 1 all over kappa times 1 over C0. Maybe I should put the 2, yeah, I want to put the 2 back over here, so put the 2 down there and just take the reciprocal of both sides. So C equivalent is 2 kappa over kappa plus 1 times C0. And as long as kappa is greater than 1, 2 kappa over kappa plus 1 would be a ratio greater than 1, which means our equivalent capacitor is at a higher capacitance than the original capacitor without the dielectric. And if you're using a dielectric with a kappa that's 1 or less, then why would you be using that in the first place? The whole point of a dielectric is to increase the capacitance. Actually, I can't think of any material that would behave in that way. I'm pretty sure, actually, I'm going to have to double check my facts on that. I don't know too much about dielectric materials, but I would have to assume that dielectric constants of less than 1 don't exist. That's what I would assume, but I'm going to have to double check my facts on that, so don't quote me on it. Okay, so that takes care of one weird case with a dielectric that's only partially filling the gap between two capacitor plates. Next up is partial filling, but in a different sense. I guess it'll make more sense once I draw it. All right. So this time This time I'm going to have a dielectric material fill the full distance from the top plate to the bottom plate, but only half the area. This time I'm going to have a dielectric material that looks like this. It's only filling up half the space between the two capacitor plates, but this time it's filling it vertically as opposed to horizontally. This is similar to, well, first off, let me define this distance as d. And this time the area is going to matter, so the area we're going to call the original area A, and this thing is going to only take up half of that area, so that thing is only going to take up 1/2 A. And I guess I'll go ahead and draw it as if it's a pair of capacitors connected in parallel. So essentially, this is like having your battery connected to a wire that splits up like this between two different capacitors, one of which has a dielectric material filling up the space between its plates. I guess I should have stayed consistent with my colors, but oh well. This is your dielectric material filling up that space. Essentially, this is what we have going on. Okay, so how do we deal with capacitors in parallel? Before we go to solving this, let's figure out how to find the equivalent capacitance for two capacitors in parallel to one another. If I have some amount of charge that gets pulled from each of these capacitors towards the battery, some negative charge gets pulled by the battery, that negative charge comes and gathers on the bottoms of those two plates, then I'm not sure how I want to word this. Then the total charge that got pulled off of each of these, it's going to be the same total that gets deposited onto the bottom side. So let's say you had a charge of Q1 worth of electrons come off of this plate, and Q2 worth of electrons come off of this plate. So you get a total charge of Q1 plus Q2, well, negative Q1 plus negative Q2, travels through this circuit, goes around and gathers on this side, so you get a total charge of negative Q1 and negative Q2 over there. So that total is constant. But what's different for these two capacitors now is going to be, well, they are going to have a difference in capacitance and they've got a difference in charge, but what will be the same about them is the change in voltage. What will be the same for both of them is the total voltage across them. So delta V1 over here is going to equal delta V2. And how do we know that? So I want to try and find a way to explain this without having to rely on Kirchhoff's rules. I guess the best way I could put it for now is that the voltage across each of these devices has to equal the battery voltage, since each of these devices individually has a direct connection to the battery. Actually, yeah. So here's the argument. These wires have to be made of conducting material, right? They have to be made of some sort of metal. And we learned before that when moving within a metal, there is no change in voltage. Right? We covered that before. We covered that, was it last week or the week before? Last week was when we did voltage. And we said when you're moving within a metal, since the electric field within the bulk of a metal is zero, the change in voltage as you integrate within the bulk of a metal is also zero. So whatever the voltage of the positive end of the battery is, that's the voltage of the positive sides of each of these capacitors. Similarly, whatever voltage the negative end of the battery is at, that must be the voltage down here. There can't be any change in voltage between this point and these 2 points, because all of those points are connected by a metal wire. Similarly, there can't be a change in voltage between the negative end of the battery and these 2 points, because all 3 of those points are again connected by a metal. So voltage at the top of each plate is the same for both plates. Voltage at the bottom is the same for both plates. They have the same change in voltage across the 2 plates. So delta V1, at least in magnitude, equals delta V2 equals delta V of the battery. And as for the reason why the battery has a higher voltage on its positive side versus its negative side, that has to do with the chemical reactions happening inside the battery. You can learn more about that in chemistry if you haven't already. But you can assume that a battery is able to maintain a difference in voltage across its 2 ends. Anyway, with this, we can come up with a relationship for the equivalent capacitor for a pair of capacitors that are connected to each other in parallel. We want to replace these with a new capacitor and this new capacitor would have to have the same voltage across it, right? The voltage across this new capacitor is still also V battery. So what can we do with this information? If the voltage across this capacitor is still V battery, let's see, rearranging the equation for capacitance, Q over delta V. I can do, if I solve for delta V, will that work? If I solve this for delta V, then I would get Q over C. So I would do Q1 over C1 equals Q2 over C2 equals Q on the equivalent capacitor over C of the equivalent capacitor. I feel like I need to replace those Q's somehow. Why am I blanking on this? This should be easy, but maybe it's just been too long of a day for me. Give me a minute to think. This isn't how I wanted to set this thing up. What am I missing? Well, if this capacitor is going to properly replace this one, then it has to have the same voltage across it, and it has to displace the same total amount of charge, right? The total charge on the equivalent capacitor would have to be the sum of the charges on the original capacitors. I feel like I'm not making this argument very well. Well, all the more reason why I should be doing this. I need to review my electromagnetism as much as you guys do. How do I make this argument more clearly? How can I justify that the total charge on the equivalent capacitor has to be the total of the charges on the originals? Well, what did I do over here? What argument did I make for this one? So I said the charges are the same. And then I created a relationship between the voltages. Right, and I argued that the total voltage needs to be the sum of the two voltages, and that's how I got this equation. Okay, so yeah, I just have to make a more convincing case that the amount of charge on this new capacitor over here is Q1 plus Q2. How do I give an intuitive justification for that, though? I don't know, maybe it seems obvious enough to some of you, but I don't feel like I've justified making this move yet. I might be overthinking things here, but usually it's because of this overthinking tendency of mine that I learn my material thoroughly enough to be able to explain it to others. So I wouldn't call it a bad thing. Can I come up with an intuitive reason for why this equivalent? Well, okay, let's go back to the definition of a capacitor. So what does a capacitor do? It separates charge at the cost of you have to create some difference in voltage between its plates. Okay, so a good capacitor is one that, a capacitor, I guess, is defined by how much charge it separates for how little cost in terms of volts that you have to give it. So an equivalent capacitor to these two would use up the same amount of volts to separate the same amount of charge. There we go. And to separate the same amount of charge, you'd have to have a charge on it that's equal to the total charge of the original two. Okay, now I feel like I've sufficiently justified it. Okay, so now we can say that Q on the equivalent capacitor is equal to Q1 plus Q2. And from there, I can do, if I solve this for Q, I get C times delta V. So C equivalent times delta V, which is just V battery, equals Q1 is C1 times, again, V battery, plus Q2 is C2 times V battery. At least for the general case. We'll deal with the dielectric case in a minute. And we can cancel this. And there we go. For adding capacitors in parallel, you simply add their capacitances. And by the way, this still works for 3 or more. So if you had 3 capacitors in parallel, it would be C1 plus C2 plus C3, and so on. And going back to capacitors in series, if you had 3 or more, it would be 1 over the first plus 1 over the second plus 1 over the third, and so on. So yeah, it still works for more than just 2, but if you do want to add them 2 at a time because it makes you feel more comfortable, then that's fine. You might get some rounding errors if you are dealing with capacitors in series, at least. So that's something you would have to watch out for. But otherwise, if you just add 2 at a time, you should still get to the same result. It'll just take a little longer because you're adding extra steps. Anyway, now that we have this formula, let's go ahead and find the equivalent capacitance for this thing. So this thing is made of 2 capacitors. Capacitor 1 is going to have a capacitance of, I'll call it C left. C left is equal to epsilon naught A over D, so that's going to be epsilon naught. The area of the left half is just A over 2 over D. Actually, wait, what am I doing? That's not what I did over here. I don't know why I'm doing it in terms of the geometry. I mean, I guess we could do it in terms of the geometry. That might lead to some interesting results, but that's a separate problem. Anyway, where were we? So I wanted to do left capacitor. Well, first of all, originally, before the dielectric was inserted, we had a capacitance of C0 before the dielectric was inserted to this thing. So what is its capacitance now? Well, for the left half, oh, actually I do still need this formula, don't I? Yeah, I do. I guess I was just thinking a couple steps too far ahead. So for the left-hand side, it's going to be epsilon naught A over 2 over D. And we know for the original capacitor, C0 was epsilon naught, just the total A over the total D. So we know that C left is equal to 1/2 of C0. Okay, that's what I wanted this for. And then for the other half, it's also going to be 1/2 of C0, but times kappa. So C right is equal to kappa times epsilon naught A over 2 over D is equal to 1/2 kappa C0. And now we can get the new capacitance. Let's do, yeah, this color will be fine. So the new capacitance, I guess I'll call it, what did I call it before? Did I call it C star? No, I just called it C equivalent. C equivalent is going to be equal to, add this to this, 1/2 C0 plus 1/2 kappa C0. So factor out the 1/2 and the C0, and you're left with 1 plus kappa. Or in other words, kappa plus 1 all over 2 C0. If kappa is equal to 1, then you're just back at the original capacitance that this thing had before the dielectric was even inserted. So this should be an increased overall capacitance for any kappa greater than 1. And again, I'll have to do some research on my own time later to see if there are materials out there with a dielectric constant of less than 1. I would doubt their existence, but I am not sure. Okay, where do I want to go from here? Are there any interesting problems we can do? Or should we just move on to another topic? Let me see. That one has concentric cylindrical conducting shells forming a capacitor. That might be worth looking at, but I feel like we've done enough with Gauss's law that we don't need this problem between previous sessions and what we did today. I think we've done enough of that. Let's actually practice with combining capacitors. So over here we've got a circuit with capacitors and a battery. So it says a circuit is constructed with 5 capacitors and a battery as shown. The values for the capacitors are all those different numbers, and the battery voltage is given. And it wants the equivalent capacitance between points A and B, which are not even marked on their diagram. What on earth? Ah, great. I knew I hated this book for a reason, and now that I'm looking at it again for the first time since years ago, I'm starting to remember why. This is one of those like mini, almost paperback books that I'm sure those of you who are in university have already encountered, where the whole purpose of the book is to just have a code that lets you access the online homework system for the course. Not the most useful book. I definitely have better books, but I use this one just because it's a little bit more compact. At the very least, it's narrowed down to the electricity topics, unlike the other book I have, which has a greater variety of topics, and it can sometimes be harder to sift through that other book. But seeing this, now I feel more incentivized to try that other book. Anyway, I'm just going to copy what they have, and I'll create my own problem out of it. So they have a battery connected to capacitor 1. which is then connected to a branching point, and on this branching point we have that is capacitor number 4. Over here we have capacitors 2 and 3, capacitor 2 and capacitor 3. That's not the best looking 3. And then those two branches reconvene at this point, and we have one more capacitor, C5, and then we route back to the battery. Okay. Do they have anything of interest mentioned here other than their very poorly diagrammed questions? I mean, how do you miss that? How do you mess that up? You ask for the capacitance between 2 points and you don't even label any of the points on your diagram. Okay, so just asking for charges and voltages on different capacitors. Okay, so pretty standard stuff, apart from when it's asking for the voltage between 2 points that they don't even specify. But let me actually go ahead and give the numbers that they have for these capacitances. So C1 is given as 4.8 microfarads. 4.8 microfarads. A farad is a coulomb per volt. If you remember the equation for capacitance, charge over change in potential, coulombs over volts, and I guess because volts are joules per coulomb, you could also think of this as, let's see, coulombs over joules per coulomb would be coulomb squared per joule, as another way you could describe a farad. But I'll just stick with coulombs per volt. Anyway, 4.8 microfarads is C1. C2 is 2 microfarads. C3 is 6.6 microfarads. C4 is 4.8. And C5 is also and C5 is also 4.8. Okay, we've got 3 of them at 4.8. C5 is also 4.8 microfarads. If a farad is a coulomb per volt, then a microfarad is a microcoulomb per volt. If you remember that, then you don't have to write out your 10 to the negative 6 to replace the micro in microfarad, so that's a little bit of advice. It's very common for capacitances to be given in units of microfarads, which shouldn't be surprising because if you've gotten this far in an electricity and magnetism course, you've probably seen charges are almost never given in full coulombs. They're usually given in microcoulombs or even nanocoulombs. Okay, so we want to find essentially the charges and the voltages on each of these. Oh, and I forgot to copy down the battery voltage is 12 volts. Battery voltage is 12 volts. Okay, let's see what we can do here. So, first combination I can make is I can combine these two capacitors in series. And while I like to do this mentally so that I don't have to redraw the circuit hundreds of times, I think for the purpose of teaching, I'm going to actually take the time to redraw this circuit over and over again. So here's C1, and then C2 and C3 are going to combine into a single capacitor that I'm going to call C23. C4 stays alone for now. And there's C5. Okay, so that's going to be the first combination we do. Next, we will be able to combine these two in parallel because any charge that gets to this point and wants to get to this point has to go through one or the other. It can't go through both. Some charge will go here, some will go here, but whichever portion of the charge goes this way cannot go that way, and vice versa. I know I already explained that before, but it bears repeating. So these are in parallel, so I can add those in parallel, and that will simplify my circuit to this. So these two now close and essentially fold into this thing, which I'm going to call C, let's see, I combined 2, 3 with 4, so I'm going to call it C234. This notation is not very helpful when you have more than 9 capacitors, because then once you start looking at numbers 10 and up, it becomes hard to tell apart, you know, something like a 10 or a 12 and a 1, 2. But usually we don't deal with that many capacitors in a single circuit, at least not for book problems, so I wouldn't worry about that too much. And C5 is still like this. There we go. Actually, let me make this one wider too. Yeah, let's make the battery a little bit wider like that. Sometimes a lot of students will make a mistake with their circuit diagrams because they draw batteries way too similar to capacitors. Make sure your batteries have a side that's clearly shorter than the other. For capacitors, the two lines are the same length, because it's supposed to represent a parallel plate capacitor, regardless of whether it's actually parallel plate or some different geometry. So it's just a pair of lines that are the same length, but for a battery you've got a short side and a long side. Make sure the long side is visibly longer than the shorter side. Anyway, back to solving this. So now I've got just 3 capacitors in series. Any charge that travels through this capacitor is going to displace an equivalent amount of charge that goes through this one, which will displace an equivalent amount of charge that will reach this one, which will push charge back to the battery. So just add those 3 in series, and our final circuit simplifies to a single capacitor C1, 2, 3, 4, 5. The combination of all 5 capacitances. Okay, now we actually need to calculate these. So, first thing we did was combine C2 and C3 in series. Adding capacitors in series, we do 1 over C23 equals 1 over C2 plus 1 over C3. So 1 over C23 equals 1 over C2 plus 1 over C3 equals 1 over 2 plus 1 over 6.6. Let's see, calculator. 1/2 plus 1 over 6.6. I'm going to put that in parentheses. And then I'm going to do 1 over that result. And I'm getting C23 is equal to approximately 1.53 microfarads. Okay, so that's C23. And then if I add it in parallel with C4, that's just direct addition. So C234 is going to equal C23 plus C4, just direct addition. And that's going to be 1.53 plus C4 was 4.8. So 1.53 plus 4.8 is 6.33 equals 6.33 microfarads. Next up is just the final equivalent capacitance, C12345. That is the result of adding these 3 in series. So 1 over C12345 is equal to 1 over C1 plus 1 over C234 plus 1 over C5. So that's going to be 1 over, what was C1 again? 4.8 plus, I would list the units, but since they're all in the same units, they're going to all come out in the same units too, so I can save myself a little bit of ink and time by not having to write the units in, since I already know they're going to come out correct. And then 1 over 6.33, and then plus 1 over, that was also 4.8, right? Yep, it was also 4.8. Okay, so 1 over, parentheses, 1 over 4.8 plus 1 over 6.33 plus 1 over 4.8. Or I guess you could also write 2 over 4.8 instead of writing 1 over 4.8 twice, but you know, no need to split hairs. So if I take the reciprocal of this sum, I get 1.74. So I get C1, 2, 3, 4, 5. Is that even visible on the screen? Is equal to 1.74 microfarads. Okay, from here we can start working in reverse to figure out the charges and voltages on each of our capacitors. So first, let me figure out what the total charge is. Since I know the total voltage is 12 volts, and I know the total capacitance is 1.74 microfarads, I can just use C equals Q over V, solve for Q. So Q would be C times V, 1.74 times 12. 1.74 times 12 is 20.88. So Q total has to be 20.88 microcoulombs. I know it's microcoulombs because I multiplied microfarads with volts. Okay, so now I know the total charge and the total voltage across our equivalent capacitor. Now let's work backwards and go here. Okay, going here, 3 capacitors that were in series added up to this. What do capacitors in series have in common with their equivalent capacitor? They share the same charge. So the charge on C1 and the charge on C234 and the charge on C5 is 20.88. So we've got Q1 is 20.88 microfarads. Q234 is also 20.88. I guess I'll write it here. Q234 is 20.88. Did I call it microfarads? Microcoulombs. 20.88 microcoulombs. And Q5 is also 20.88 microcoulombs. Okay. Next up, we unpack... Oh, actually, wait. We can calculate the voltages across each of these. So C equals Q over V. You can rearrange that. V equals Q over C. Or, well, delta V equals Q over C. But, you know, again, no need to split hairs. Let's switch to this color since I haven't used it at all on this page. Q over C. So 20.88 microcoulombs divided by C1, which was 4.8. So 20.88 divided by C1 is 4.8 gives me 4.35. So I guess I'll call it V1 equals 4.35 volts. Okay, and then for 234, the capacitance was 6.33, so Q over C, 20.88 over 6.33 gives me about 3.298, so 3.30 volts. This one, I guess, where do I even want to write it? I guess I'll write it here. V234 equals 3.30 volts. And then for V5, we're going to do Q over C again. 20.88 over C5 was also 4.8. So actually we can just copy this one. It's just 4.35. No need to do the same calculation twice. All right. Now we can unpack C234. We said when deriving the equation for capacitors in parallel that the voltage across them must be the same. Delta V1 equals delta V2 equals delta V, well, in this case it's not delta VB, it's delta V between, I guess it's delta V between the bottom of C1 and the top of C5. Delta V from, I guess I'll use different colors. So this point and this point and this point are all connected by metal, so they must be at the same voltage. There must be no change in voltage across them there. And then this point and this point and this point must all be at the same voltage because, again, they're connected by metal. And there is no net electric field in the bulk of a metal conductor. So no change in voltage. So yeah, the voltages across parallel capacitors must be the same. The change in voltage across parallel capacitors must be the same. So the voltage across C234, the 3.30 volts, must be the voltage across each of these. So I'm going to go ahead and say that C4 and C23 will have voltages of V4 equals 3.30 and V23 is 3.30 volts. And from there, I can calculate the charge on each of them. The charge on C4 is going to be, let's see, C equals Q over V, so C times V equals Q. So Q4 is equal to C4 times V4. And C4 was 4.8, so 4.8 times 3.30 is 15.84 microcoulombs because I multiplied volts with microfarads. And then Q23, where am I even going to write this? I'll write it down here. Q23, and then I'll just have an arrow pointing. Q23 is going to be C23, which was 1.53, times V23, which was 3.30, and that gives me 5.049. I'm going to round it to 5.05, just because everything else we've had so far has been kept to 2 decimal places or less. So that's going to be 5.05 microcoulombs on capacitor 2.3. And finally, we unpack capacitor 2.3 into the original C2 and C3 that it was before we combined them. And let's see, capacitors in series share total charge with their equivalent capacitor. So C2 must be 5.05 and C3 must, or not, Q2, I should say, and Q3 must each be 5.05. So Q2 and Q3 are 5.05. Q2 is 5.05 microcoulombs, and Q3, same deal, must be 5.05 microcoulombs, and now we just need to find V2 and V3. Okay, V2 can be calculated from, let's see, so C equals Q over V, which means V equals Q over C. So 5.05 over C2, 5.05 over 2 is 2.525, and I'll round it to 2.53. 2.53 volts must be V2. V2 equals 2.53 volts. And then for C3, which is 6.6, we do 5.05 over 6.6, and I'm getting 0.765. I'm going to round that to 0.77, so V3 is 0.77 volts. That's not the best place to write it. I'll write it a little bit higher, 0.77 volts. Okay, yeah, that's a little bit better. At least it's a little more visible. And there you go. We have figured out the voltages across and charges on each of our capacitors. C1 has a charge of 20.88 and a voltage of 4.35. And a all the capacitances were given, so we don't need to restate what was already told to us. C2, we now know the charge and voltage on it. We know the charge and voltage on C3. We know the charge and voltage on C4. And we know the charge and voltage on C5. Yep, we got all of them. Another thing you might have noticed is when we unpacked things in series, you might have noticed that the voltage across this one, 4.35, plus 3.30 plus 4.35 should add up to approximately 12. Let's go ahead and check that. 4.35 plus 3.30 plus 4.35 again is exactly 12. Yeah, so capacitors in series, their charges are the same, their voltages add to the total voltage across their equivalent capacitor. And then when you unpack something in parallel, the voltages are the same, but the charges add. 15.84 plus 5.05 is 20.89, which is approximately the 20.88 that we started with before we unpacked C234. Of course, there are going to be some slight errors because of rounding, but overall, that's another way you could solve these. If you remember that voltages add for capacitors in series and charges add up for capacitors in parallel. That gives you a couple more options in case you felt that my way of doing it was too slow. But yeah, I think this is a pretty good stopping point for us for today. I don't know if next time I'll continue with resistors or if I'm gonna go ahead and do some more mechanics instead and just put electricity and magnetism on pause. The AP exams are about a month away now, so with the majority of physics students being students in mechanics, I feel like it might be better to focus on mechanics for the next few weeks, but we'll see. I'll probably change my mind a couple times over the course of the week, and whatever happens next week happens. Of course, if you show up and ask questions, then we can do that instead. We don't have to stick to an agenda, but I'll have something planned for next time anyway, just so that I'm not stuck with nothing to do if nobody is here to ask questions. And yeah, I think that's all I have to say. Take care, and actually, there is one more thing. I've decided that, I'm going to postpone this by another half hour. So this time, for sure, this will be the last time, at least I hope, this will be the last time I have to readjust the schedule for office hours. But I do think that I need the full 2 hours between the gaming stream and the office hours stream, just to get things done in between, because an hour wasn't enough time, and now I'm realizing an hour and a half still isn't enough time either to get anything meaningful done in the time between. So starting next week, it'll be half an hour later from what it has been for the past 2-3 weeks now, whatever it was. You'll see the changes reflected on the schedule on Twitch, and that'll be that. Now for real, take care, and I will see you next week.